Math 3 Lesson Summary Video. Shift and Stretch. This lesson is a Solidify Understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to apply transformations to the rational functions in order to create a graph, as well as apply the concepts of transformations to write the equation for a rational function given the graph. The lesson begins with looking at the parent graph for the rational function and identifying some of the key features needed in order to do transformations. So when we look at the parent graph, things that we want to identify are where are the horizontal asymptote and the vertical asymptote. So we learned yesterday in our lesson that we have that horizontal asymptote right here at the x-axis, which is the equation y equals 0. And then we have the vertical asymptote here at the y-axis, which is the equation x equals 0. Anchor points. What we're talking about here are points on the actual graph that we can use as references to do all of our transformations, to do our translations, our reflections, our stretches. And so when we look at the corner, that's one of the easiest points to deal with. We have the point 1, 1, and the point -1, -1. Most rational functions are dealing with a lot of fractions, so you are going to have a couple of points that aren't exactly on a corner point or on a grid, but half is usually the easiest one to deal with. So if I do 1 divided by 1/2, I get 2. And same thing for negative. If I do -1/2, 1 divided by -1/2 is -2. And if I do 2, 1 divided by 2 is 1/2. And 1 divided by -2 is -1/2. So those give you 3 pretty little points in the corner that you can use to do all of your transformations, to slide, stretch, and to make sure that you have a really pretty curve going down to those asymptotes. Now, when we look at the next page of the task, this task is having you to apply transformations. Now, you did transformations last year, but this time, instead of starting with the graph, it's actually giving us the graph, and we want to try and write the equation that would go with that graph. So when I look at this graph, the first thing I notice is that its horizontal asymptote is not on the x-axis. It has definitely shifted up. Now, the vertical asymptote still seems to be right there on the y-axis, so there is no left to right shift. So when I think about my parent function is f of x equals or y equals 1 over x, if it was shifting left to right, I would have to put something down here in the denominator with x. But it's not. It's on the outside, and it's shifting up, so I'm going to add, and it's 1, 2, 3, 4, 5. So this would be the equation that would have a horizontal asymptote at 5, a vertical asymptote at 0. It went 1, 1, so that anchor point was still 1 away from the vertical asymptote and 1 up from the horizontal asymptote, so it wasn't stretched any. And so this would be my equation. Looking at this version, thinking of y equals 1 over x, it still has a vertical asymptote at 0. And it still has a horizontal asymptote at 0. So it has not actually shifted left or right any, or up and down any. So I haven't added or subtracted anything from it. My distance from the asymptote still 1, 1, and -1, -1, except it's no longer in the upper right corner and lower left corner. It's been flipped. We know that's a reflection. Now, if I reflect it over the x-axis, I know that to do that, I have to multiply outside the function by -1. So if I put a negative out here, that should flip this down to the bottom and flip this one up to the top. Going over to this one, things that I'm looking for. I see that my vertical asymptote has shifted. Yep, not on the y-axis anymore. It has shifted to the right. My horizontal asymptote is still on the x-axis though, so it hasn't moved. So when I do my shift, I remember, okay, Going to the right is actually subtraction. So I'm going to do x minus 2, but I am going to keep it in the denominator. Remember, when we use these fraction bars, that is a type of grouping symbol. We always think of parentheses as grouping symbols, but this big bar is a grouping symbol. It's grouping everything in the denominator and the numerator into their groups. So it is a grouping symbol. So to be inside the function, I need to be inside the denominator. It didn't shift up and down any. So no addition out here. It didn't get flipped, so don't have to worry about multiplying by a negative, and it is still 1 over and 1 up from the asymptotes. Now you need to go through and finish practicing all of the other graphs that it wants you to do. It's got some multiple choice where you can match and try to remember all of your transformations from Math 2. And then when we get to number 11, this time it's giving us the equation and it is asking us to go about graphing it. So when I look at this particular equation, I want to identify what are the transformations that are happening. So it's subtracting inside the denominator. So that is going to make me go to the right 4 spaces. Now don't get confused that this is up front. What matters is that it is outside of the function. If it is outside of the function, then it's doing some kind of up and down shifting. Also, don't get confused by this plus sign. It's the number that tells us how it's going to shift. And this is a negative 2. So that means that it is going to shift down 2 places. So I want to get my asymptotes up there first because they kind of give me the fences that keep my graph together. So if I move to the right 4 spaces, I look at my graph and it seems to be counting by 2's. So 2, 4. So that'll give me a vertical asymptote here at 4. And I'm shifting down 2. So it won't be at 0. I'm going to be down at negative 2. This gives me my crossbars. Now, I do have one other transformation happening here. I have multiplied by 3, so this is going to be a vertical stretch. Remember, that just changes the up and down number. So for my, and when we do our anchor points, remember we're counting from where the asymptotes cross, not necessarily the origin, 0, 0. So instead of going over 1 and up 1, I'm going to go over 1 and up 3 because I have to do 1 times 3. So over 1, up 3. If I went over 1/2, instead of going up 2, I'm going to go up 6. So over 1/2, 2, 4, 6. All right. And instead of going over 2 and up 1/2, 1/2 times 3 is 3/2. So that's like 1 1/2. So over 2, up 1 1/2 is going to be about right there. And that's going to give me the 3 points I need to get my graph drawn in here. Over here, I do the same thing. It was 1, 1, but now it's going to be 1, 3. 1/2, 6. And 2, 3/2. And so that just stretched it a little steeper onto my graph. The very end of the lesson is asking us to sum up what all of these transformations did to our function. If we have this very generic equation where we don't actually have numbers in here, but we're just thinking about what happens if I do subtract something, what happens if I do add something, what happens if I do multiply by something, what kind of effect does that have on the key features of the graph? So if I think about my vertical asymptote, that's the one that goes up and down, shifting a vertical line up and down doesn't change anything, but shifting it left and right does. So it's going to be the left-right shift that affects the vertical asymptote. So my vertical asymptote is always some equation x equals, it's usually x equals 0, but if I shift it to h, then it's always going to be x equals h. Likewise, the horizontal asymptote, taking a horizontal line and shifting it left to right doesn't do anything, it stays at the same place. But shifting it up and down does do something to it. It's going to change it from where it is. And it was originally at 0, but now it would have shifted to wherever k is. Now, our vertical stretch factor is always this number up here because it's generically supposed to be 1. So if b is something other than 1, we have been stretched. So whatever that top number is, it's telling us what we are stretching by. If we think about domain and range, we know domain goes from -infinity to 0, and then 0 to infinity, and range goes -infinity to 0, and then 0 to positive infinity. But it's not always 0. The domain is always leaving one number out, and that number is always the vertical asymptote. So if my vertical asymptote is at h, then instead of being 0, I want this to be h. My horizontal asymptote is always everything except where the horizontal asymptote is. That's the range. That's what's getting left out of the range. So if it's not 0, if my horizontal asymptote is k, then the range is going to also leave out k. So that's how we can find, looking at any equation, we can find these things. The thing to remember about anchor points is that we're always counting from our vertical and horizontal asymptote. So it's going to be 1, 1 unless it gets shifted. But it's always going to be 1 away from that vertical asymptote. So it's always going to be 1 plus h, or -1 plus h, because I'm going to count 1 away from wherever h ended up being, 1 to the right and 1 to the left. And so I always stay 1 away from that vertical asymptote. We also know that this number should always be 1 unless we multiplied it by something. The example we did, we multiplied by 3. So I'm going to always end up taking 1 times b, or -1 times b. But I also know that I'm counting from the horizontal asymptote. So I'm going to count from k to figure out what that is. So this kind of generalizes what do these transformations do to the key features of the graph.